Hello, this is Irene from Exam Help Lab. Today I'll be solving Chemistry Paper 2 AS Level Structured Questions 9701 Paper 2, Variant 3, May, June 2018. Question number 1. The elements sodium to chlorine in the third period all form oxides. Draw a diagram to show the shape of the molecule of each of the oxides SO3 and Cl2O. Name each shape. In SO3, each oxygen atom forms a double bond with the sulfur atom. So sulfur in the middle, it will be sharing 2 of its electrons with each of the 3 oxygen atoms. And then there are these lone pair of electrons of the sulfur, where repulsion between these 2 lone pairs will be greater than that between the lone pair and each of these 3 bond pairs. The shape for this SO3 structure would be triagonal planar. Now coming towards Cl2O, just like H2O, where oxygen shares 2 electrons with 2 hydrogen atoms and 2 lone pairs are left on oxygen, Cl2 has oxygen's 2 electrons being shared with 2 chlorine atoms, and it has a bent shape. So O in the middle, it will be having a single bond with each of the 2 chlorine atoms and 2 of its lone pairs. Again, repulsion between 2 lone pairs will be greater than repulsion between a lone pair and a bond pair. B part 1. Explain why the melting point of MgO is higher than that of Na2O. So MgO has stronger ionic bonding due to greater nuclear charge on Mg, which is Mg2+, as compared to that on Na, which is Na+, just single +1. And when charge density is greater on Mg ion, that requires higher melting point or higher energy to break those bonds. So we can write that MgO has stronger ionic bonding, which is due to the nuclear charge on it, and charge density is higher on magnesium ion. But to explain why the melting point of silicon dioxide is much higher than that of sulfur trioxide, so silicon dioxide, like diamond, has got giant molecular structure and strong covalent bonds that have more strength than the intermolecular forces present in the structure of sulfur trioxide, and those intermolecular forces are van der Waals forces. So I can write that silicon dioxide, first of all, has giant molecular structure, while sulfur trioxide has a simple molecular structure. And the second point would be that SiO2 has covalent bonds that are stronger than van der Waals forces in SO3. Part C. Sulfur trioxide is produced by the reaction between sulfur dioxide and oxygen in the contact process. A dynamic equilibrium is established. Part 1. Explain why increasing the total pressure at constant temperature increases the rate of production of sulfur trioxide and increases the yield of sulfur trioxide. So rate of reaction increases because when greater pressure is applied, molecules, they get closer to each other, which increases chances of successful collision. So we can write that molecules get closer to each other, and that increases the chances or the frequency of collision. And those 2 successful collisions. Now, talking about the yield of sulfur trioxide will increase because increasing pressure will shift equilibrium to the side with fewer moles. Now, on the reactant side, we have got 3 moles, while on the product side, we have got 2 moles. Now, if we increase the pressure, the equilibrium will shift towards the side that has a fewer number of moles, and that is towards SO3. So that will increase the yield of SO3. So we can write that fewer moles on the right side, this equilibrium shifts towards the right, and that favors the formation of sulfur trioxide. The graph shows how the concentrations of all three species in the system change with time for a typical reaction mixture. The gradients of all three lines decrease with time and then level off in this dynamic equilibrium. To explain why the gradients of the sulfur dioxide and oxygen lines decrease with time. So gradient of concentration versus time graph is rate. As it can be seen from this graph, that rate is decreasing for both sulfur dioxide and oxygen. That is the gradient with decrease in their concentrations. So I can write that the gradients there are decreasing with increase in time, and the reason to that is rate is decreasing with decrease in concentrations of sulfur dioxide and oxygen. So initially the rate was much higher, but with increase in time, the rate starts to decrease. Part 3 explain why all three lines become horizontal. So because that's when dynamic equilibrium is achieved. That's when rate of forward and backward reaction is equal. So we can write that rate of forward and backward reaction gets equal. That's when the gradient gets 0. That's when it gets horizontal. The graph gets horizontal. Part 4 suggests a reason why the initial gradient of the sulfur dioxide line is steeper than that of the oxygen lines. Because if you see this equation over here, the mole ratio of sulfur dioxide to oxygen is not equal. In fact, relatively more sulfur dioxide is being used up in this reaction. So that's the reason why the graph is steeper for sulfur dioxide. This is all due to the mole ratio that is present in the equation. So we can write that there is 2:1 ratio in the equation, which causes this change in steepness of the graphs of SO2 and oxygen. Part D, 2 moles of sulfur dioxide and 2 moles of oxygen are sealed in a container with a suitable catalyst at constant temperature and pressure. The resulting equilibrium mixture contains 1.98 moles of sulfur trioxide. The total volume of the equilibrium mixture is 40 decimeter cubes. Write the expression for the equilibrium constant. Okay, so Kc is equals to concentration of the product, and it should be raised to the power of the number of moles it has in the equation. So SO2 divided by the concentration of the reactants, and it should be also raised to the power of their number of moles. So this is the Kc equation for this reaction. But to calculate the amount in moles of sulfur dioxide and oxygen in the equilibrium mixture. Okay, for this part, you gotta draw the following table. You should be writing the main equation first, which is 2SO2 plus O2, the reversible sign, and then 2SO3. Initial, meaning initial number of moles, change in number of moles, and then moles at equilibrium. Now, initially there were 2 moles of sulfur dioxide according to the information which is given in the beginning of discussion, that there were 2 moles of SO2 and 2 moles of O2 in the sealed container reacting. So 2 moles of SO2, 2 moles of oxygen, and initially there were 0 moles of SO3 before the start of the reaction. Later it says that the resulting equilibrium mixture contains 1.98 moles of SO3. So at equilibrium we have 1.98 moles of SO3. So there was an increase of 1.98 moles to SO3. This means that SO2 and oxygen must have decreased in some amount, but by what amount we have to take that into consideration first. Since mole ratio of sulfur dioxide to sulfur trioxide is equal, that is 2:2, now sulfur dioxide must have decreased by the same amount that sulfur trioxide has increased by. This means that the number of moles will decrease by 1.98. So at equilibrium, we will be having 0.02 moles of sulfur dioxide. Now coming towards oxygen, mole ratio of oxygen to sulfur trioxide is 1:2. This means that oxygen will be decreasing by half of the number of moles which sulfur dioxide had decreased by. So 1.98 divided by 2, that is 0.99. So there will be a decrease of 0.99 from the initial number of moles of oxygen. We will be left with 1.01 moles of oxygen at equilibrium mixture. So in the equilibrium mixture, we will be having 0.02 moles of sulfur dioxide and 1.01 moles of oxygen gas. Now part 3, use your answers to the part 1 and part 2 to calculate the value of Kc. So Kc is equals to concentration of sulfur trioxide to the power square. Now we need to find the concentration, while these were the number of moles that we got. So number of moles divided by the volume will give you the concentration. So 1.98, which were the number of moles of sulfur trioxide in equilibrium mixture, divided by the total volume of the container that was told to us in the beginning, that the equilibrium mixture has a total volume of 40 centimeter cube. So divided by 40 raised to the power square, and then 0.02, that were the number of moles of sulfur dioxide, again divided by 40 square, multiplied by the number of moles of oxygen divided by the total volume. And then this way we get Kc as 3.88 into 10 to the power of 5, and the units will be per mole decimeter cube. Question number 2, one reason for the wide variety of organic compounds is isomerism, either structural isomerism or stereoisomerism. Explain the meaning of the term structural isomerism. So these are the molecules that have same molecular formula but different structural formula. But to explain the meaning of the term stereoisomerism, so these are the molecules that have same molecular and structural formula but have differently arranged atoms in space. Part B, Pant1E does not show stereoisomerism. Give 2 reasons why Pant1E does not show stereoisomerism. Now, there are 2 stereoisomers. First is geometrical isomers, that is cis or trans isomers, that require each carbon atom of C to C double bond to be bonded to 2 different atoms. But here, this carbon atom, which has a double bond to other carbon atom, this carbon atom over here is bonded to 2 same atoms, that is hydrogen atoms. So this is not a geometrical isomer anyways. This does not show stereoisomerism, and the first reason to that is because this carbon atom is bonded to 2 hydrogen atoms. So we can write that carbon in C to C double bond is bonded to 2 hydrogen atoms. The other is optical isomerism, that has a central carbon atom and it should be attached to 4 different atoms. Do you see any carbon atom in this structure that has a central carbon atom and that central carbon atom is bonded to 4 different atoms or group of atoms? No, there isn't. So we can write that no carbon atom is bonded to for different atoms. Part 2. Structural isomer of pentwanene is used as the monomer to form a polymer. The repeat unit of this polymer is shown. Draw the displayed formula of the monomer used to make this polymer. Give the name of the monomer. So monomer is just going to be having a double bond in the middle of these two carbon atoms here, and these two bonds will be removed. The rest will remain the same. So C to C double bond, H over here, another H. Here we will have an ethyl group, and here we will have an methyl group. And it's going to be 2-methyl but 1-ene. That is because the longest carbon chain is going to be this one. We'll start labeling from here to give the least number to the functional group, that is this double bond. So 1, 2, 3, 4. We have the methyl group attached to the second carbon atom, and we have the double bond between the first and second carbon atom. But we are going to give the least number possible in its name to the double bond. So it's going to be but 1-ene, not but but 2-ene. Part 3. A different structural isomer of pent-1-ene shows geometrical isomerism. Draw the structure of one of the two geometrical isomers with the formula C5H10. So we are going to either have to draw the cis isomerism or trans isomerism. So we will be drawing the cis structure. We'll have the methyl attached here and the ethyl group attached here, while we will have hydrogens on the top. And the name to this is cis 1, 2, 3, 4, 5. So it's going to be pent-2-ene. Question number 3. The elements in group 17, the halogens, show trends in both their chemical and physical properties. The elements and the compounds have a wide variety of uses. Part 8. At room temperature, fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. Part 1. State the trend in the volatility of the group 17 elements down the group. So volatility decreases down the group. And in the next part, they're asking you to reason this trend. Now, the reason to this is that this is due to increase in number of electrons from fluorine to iodine, which increases strength of van der Waals forces. So write that number of electrons increase down the group, which increases strength of van der Waals forces. Part B, iodine can be displaced from sodium iodide by chlorine. Write an equation for this reaction. So sodium iodide plus chlorine, that gives sodium chloride plus iodine. This happens because a more reactive reagent can displace the less reactive one from its solution. Here, chlorine is more reactive than the iodine. Part C, silver nitrate solution is added to separate solutions of sodium iodide and sodium chloride. Precipitates form, an excess of aqueous ammonia is then added to both precipitates. Complete the table to give the color and the name of the precipitate formed in each reaction and the effect of the addition of an excess of aqueous ammonia to each of the precipitates formed. So iodide ion gives yellow precipitate with aqueous AgNO3, and that precipitate is silver iodide, which if added to dilute ammonia doesn't dissolve, so we're going to write that no visible change. Now chloride ion gives white precipitate with aqueous AgNO3, and that PPT is silver chloride, which if added to dilute NH3, it dissolves. Part 2, write an ionic equation including state symbols to show the reaction occurring when AgNO3 is added to NaI. So for this, first of all, I'll write the main equation. AgNO3 in aqueous state plus sodium iodide in aqueous state. This forms a precipitate, and that precipitate is silver iodide. And precipitates are in solid form plus sodium nitrate, that is also going to be in aqueous state. Now you need to break all these down into their ions, leaving behind only the solids. You will only break down those substances which are in aqueous state. So AgNO3 has Ag plus and NO3 minus. NaI has Na plus and I minus. AgI will remain as it is because it's in solid state, and Na plus in NO3 minus. Now you need to cancel out all those which are common on both sides. So Ag plus is though common, but we have not divided AgI into Ag plus and I minus. So Ag plus cannot be cancelled from the left side. NO3 minus and NO3 minus can be cancelled. Na plus and Na plus can be cancelled. So our main ionic equation for this reaction would be involving all those which are left over, Ag plus I minus, that gives AgI. And don't forget to mention the states. So this is in solid state, this is going to be in aqueous state, and this will also be in aqueous state. Part D, solid sodium iodide reacts with concentrated sulfuric acid to form purple fumes of iodine and hydrogen sulfide gas. However, when solid sodium chloride reacts with concentrated sulfuric acid, the only gas produced is hydrogen chloride. Explain the difference in the reactions of concentrated sulfuric acid with sodium iodide and with sodium chloride. Your answer should refer to the role of the sulfuric acid in each reaction. Okay, so when sulfuric acid reacts with sodium chloride, the product forming is HCl, and Cl minus, that is the chloride ion, has got more oxidizing power than H2SO4. So the reaction doesn't go any further. But when sulfuric acid reacts with sodium iodide, the product that is forming is hydrogen iodide, and iodide ion has more reducing power than H2SO4, and it gets further oxidized by H2SO4 to iodine and hydrogen sulfide gas. Now, so we can write that chloride ion is more oxidizing than H2SO4. That's why the reaction doesn't proceed any further, while I minus ion or iodide ion is more reducing agent than H2SO4. That's why H2SO4 will again react with Hi, which had formed when NaI has reacted with H2SO4 to form iodine and hydrogen sulfide. And we also need to refer to the role of the sulfuric acid in each reaction. So sulfuric acid acts as an acid when reacting with NaCl, and it acts as an oxidizing agent when reacting with sodium iodide. Part E, chlorine is commonly used in water purification. When chlorine is added to water, it reacts to produce a mixture of acids, one of which is chloric acid, a powerful oxidizing agent. Part 1, explain the meaning of the term oxidizing agent in terms of electron transfer. So oxidizing agent gets reduced in a reaction that is gained in electrons. So oxidizing agent gains electrons. Part 2, suggest an equation for this reaction of chlorine with water. So chlorine plus water. One of the products is HClO, that is chloroquine acid, and the other product is simply hydrochloric acid. Part 3, write an equation for the reaction of chlorine with hot aqueous sodium hydroxide. Use oxidation numbers to explain why this is a redox reaction. So, reaction between chlorine and hot aqueous sodium hydroxide gives sodium chloride plus NaClO3 plus water. Here chlorine has an oxidation number of 0, -1, and +5. Use oxidation numbers to explain why this is a redox reaction. So here chlorine is getting reduced from 0 to -1 and getting oxidized from 0 to +5. And a redox reaction is when oxidation and reduction both take place simultaneously in the same equation. So we can write that chlorine gets reduced from 0 to -1 and oxidized from 0 to +5. Question number 4a is CH3CHBr, CH2CH3. Some reactions of A are shown. So reaction 1 is a substitution reaction where Br gets replaced by OH. Reaction 2 has the same reagent as that of reaction 1, but the only change will be the condition this time. NaOH over here will be in ethanolic state, while in the reaction 1, NaOH will be in aqueous state. Part 1, name A. Name A. A has Br attached to the second carbon atom, so this is 2-bromo, and the straight chain is 1, 2, 3, 4. The straight chain contains 4 carbon atoms, so that will be butane, 2-bromobutane. Part 2, name the class of compound to which B belongs. So secondary alcohol over here and the oxidizing agent reacting with it. This means that a B must be ketone. Part B, there are 3 structural isomers of A. Draw the structures of these 3 isomers of A. So other than A, we have got 3 other structural isomers to this. So A has a molecular formula of C4H9Br. We can have Br attached to the first carbon atom. So Br over here and rest of them hydrogens. The second structure could be that A already contains Br attached to the second carbon atom. So what we can do here is we can have a methyl group attached to the second carbon atom while having Br attached to the first carbon atom. So Br over here will be having a methyl group attached to the second carbon atom. So remaining will be H. And the third one will be having a tertiary halogen alkane where we will have this carbon atom attached to Br and 3 other methyl groups. Okay. Part C, reaction 1 occurs by 2 different mechanisms at the same time. These mechanisms are referred to as SN1 and SN2. State what the letters S and N represent in the abbreviation SN1. S represents substitution, and N represents nucleophilic. Part 2, complete the SN1 mechanism for reaction 1. So SN1 mechanism has got an intermediate product always having a carbocation, that is carbon atom with positive charge on it, not partial positive charge but complete positive charge. So we will start with giving partial charges to this C to Br bond, which will break heterolytically, and we will have an arrowhead towards Br, and NaOH will also break heterolytically with Na having a partial positive charge and OH with negative charge, and again an arrow. The carbocation, in which will be an intermediate, will have a carbon with positive charge. So this carbon atom will have a positive charge, and OH negative with a lone pair of electron will be attracted towards this positively charged carbon atom. Part D, the SN1 mechanism for reaction 1 is repeated using CH3CHCl, CH2CH3, or CH3CHI, CH2CH3 in the place of 2-bromobutane. State and explain how the rates of these 2 reactions will compare with the rate of the original reaction using 2-bromobutane. So what I can write is that CH3CHCl, or 2-chlorobutane, this reaction will be much slower then 2-bromobutane, and 2-iodobutane reaction will be faster than 2-bromobutane. That's because C2Cl bond is stronger than C2Br bond, and C2I bond is weaker than C2Br bond. That's why it breaks much faster. Part E, reaction 2 uses the same reagent as reaction 1, but under different conditions. State 2 differences in the conditions needed to ensure that reaction 2 is more likely to take place than reaction 1 when this reagent is added. So reaction 1 and reaction 2, they both are going to use the same reagent, that is NaOH. The only thing which will be differing is in the conditions, and one of the conditions is that in reaction 2 we'll be using ethanolic NaOH over aqueous NaOH, and the second one we will have to put that heat under reflux in reaction 2 to make sure that C4H8 forms out of 2-bromobutane. So the first condition would be ethanolic NaOH. The second one is heat under reflux. That was the end of the paper. Thank you for watching.